Oh boy. Oh boy, oh boy, oh boy, guys. I'm pretty upset. So I recorded class. I held class 9:30 to 10:45, and when Canvas went to save my video, it saved it, I guess. I don't know. Didn't look like it saved it. It opened the folder and there was no file there. I did a Control F search for the file. It doesn't exist. So Canvas deleted my hour and 15-minute video. So that's fantastic. So if you didn't catch the live video, if you're rewatching, this is news to you. But most of you did not watch it, I would say, live, which is going to kind of represent how that's a problem, because you are now going to get a much quicker, much more abbreviated version of this section, because I do not have time between now and my next class to do the whole thing. Unfortunately, the time doesn't exist. So this is going to go quicker. I'm going to just you're going to see a lot of the notes I already wrote. I'll pull up a calculator and explain some things here and there. But guys, this is just one of the many joys we have for this kind of thing. All right, so, and super quick. Today's date, homework, my math lab that's due. Video quiz, yes, video quiz, yes, video quiz, yes, video quiz. So you're going to go into Canvas and you're going to download that file under the quizzes that says video quiz chapter 6-7. It's due by the 27th by midnight. No late exceptions will be accepted, especially if you're just not watching the videos on time. There is a separate section under the quizzes where it says submit here. So what you're supposed to do is download the Word file, put your answers in the Word file, and submit that saved document to where it says submit here. That's where I'll grade it, and then you'll see your grades under your assignment grades, not necessarily the quiz sections. Excel, next one that's due. 5.2 population. Then the one after that, this is probably going to be our last one, mutual fund. It says like 9.2-9.4 because it's the second Excel homework, but it relates to section 9.4. The formula sheet is in Canvas under the reviews. The final exam is likely to only be one day only, not this several days stuff, which I guess doesn't really matter since most of you are just opening it on the last day and doing it then anyways. You will get a review. Your projects are graded. I made little notes about it. All right, so let's move on. Continuing 6.2, where we left off. All right, so we did this with Excel last time. We did this for compounding annually only, and we saw that 1, 5, 10, and 40 years in. I skipped the 5 years for this. I just did 1 years, 10 years, and 40 years. So we got the same person, Bob. He's going to put 10,000 away at 2% interest, but instead of compounding annually, we're going to compound monthly now. How much money does Bob have after 1, 10, and 40 years? How does this compare to when he compounded annually? So you're going to see some red notes over here, and that relates to the compounding annually. I will pull out the calculator to show one of these calculations, but not the rest. Again, I've got to do this really quickly. I don't have a full hour and 15 minutes. I've got like 20, 30 minutes, but you'll get all the information. I just won't repeat myself. You'll probably have to pause a little bit more. So our principal given, $10,000. Our interest rate, 2%. Convert it to a decimal, 0.02. Time, we have 3 different cases, 3 different problems, 1 year, 10 years, 40 years. But now we're compounding monthly, which means we're using a different formula. We're using this formula right here. This is compounding anything besides annually. This is compounding annually. It has an extra couple of pieces in the formula. It has an over in inside and an in next to the t. See, here's the over in, here's the in next to the t. Always make sure you pre-multiply that exponent. Then it's just cookie cutter, plug and chug. You put the numbers in, you pull out a calculator, you let your calculator think for you. So for the 1 year case, the principal's 10,000, parentheses, 1 plus r over n. So that's, 1 plus 0.02 over 12. Again, literally just plugging them into a formula. Let me write the formula up here just in case. No, that's highlighter. A equals P, parentheses, 1 plus R over N raised to the NT. The annually, which will be used for the red down there, that's A equals P, parentheses, 1 plus R to the T. That's the difference there. So we're compounding monthly, 10,000, 1 plus 0.02 over 12, because there's 12 months in a year, raised to the 12 times 1. We go ahead and multiply the exponent. 12 times 1 is 12. And then we just put this in a calculator. So here's a calculator. You can see all the other stuff we were doing in class. 10,000 times, you may actually have to hit your times key like this. I don't, I just have to open a parentheses, but you may have to do the times. So I'll do it for this one. 1 plus 0.02 divided by 12, close the parentheses, raise it to the 12. And I've explained why you have to pre-multiply before. If you do this as 1 times 12, it's going to spit out a wrong answer, but this is the right answer. $10,201.84, which is right here. If you had done this as a compound annually, so we're not saying we gain money every month, we just gain it every year, the 12s don't exist in that. So it's 10,000, we're using the red formula. 10,000, open a parentheses, 1 plus 0.02, close it, raise it to the 12. Sorry, not 12, 1, excuse me, 1 year. And we get 10,200, a number we saw last class. So what I'm trying to emphasize here is we've gained an extra $1.84 by compounding monthly over annually. The more you compound, the more money you make, but it's a subtle change. Then, if we go to the 10-year scenario, so now Bob's money has been put away for 10 years. So this is now 12 times 10 instead of 12 times 1, which is 120. That means we're getting money 120 times. When you put this in your calculator, you end up with $12,211.99. Versus when we did 10 years compounding annually, it was $12,189.94, roughly a $20 difference. So again, you're gaining a little bit more money by accruing money more frequently. But is it a significant amount of money? No, it's another 20 bucks. Not the end of the world if you're missing that 20 bucks, but it's nice to have. Then for 40 years, our exponent's now 12 times 40, which is 480. When you jam that in a calculator, you'll get $22,240.59, which is still relatively close to what we had originally when we compounded annually, $22,080.40. So now it's an extra, what is that, like 160 bucks, something like that. I may have even said $60 in the previous, but that's 160. So this follows something known as what we call diminishing returns. The more frequently you compound, you gain more money, but not significantly more. And as you compound more and more and more, that effect becomes less and less and less. You're still gaining more, but less. So let me just with a calculator, because I didn't write that part down, I'll show you, what if we compounded daily? So if we did 10,000, parentheses, 1 plus 0.02, divided by daily. So I'll skip the banker's rule and just use 365. And then raise that to the NT, 365 times 1 is 365. So this is us gaining money every day instead of every month. And that gives us $10,202 and a penny versus the $10,201.84 or the 10,200. So you can see compounding once per year, we get 10,200. Going 11 more times to 12 times total gains us an extra $1.84. Going to 365 times, which is another, 353 times, only gains us another, 16.8, so that's 24 cents. By going from 12 to 365 times, you only gain an extra, again, 24 cents. That's diminishing returns. I did this Dorito relationship to diminishing returns. Don't have time for it, unfortunately, but basically it just says, first chip is delicious, you're getting something out of it. Your 12th chip is delicious, but a little less so. Your 100th chip is still good, you're still eating it, so you must be getting something out of it, but you're not as happy eating that 100th chip. That's diminishing returns. All right. Sorry, I'm doing this on the fly. I really am. It's kind of unfortunate. Yes, that's it for the section. So 6.2, exponential functions. We already talked about exponential functions, but this is going to put them in the continuous model. The only reason we look at this is because of Excel. We as quantitative students have no reason to deal with a continuous model. We're perfectly fine with those two equations we already saw. The A equals P parentheses, and 1 plus R to the T, or 1 plus R over NT. 1 plus R over N raised to the NT. Those are on your formula sheets. You don't have to memorize them. The continuous growth model is the only thing that Excel can use. It doesn't know what you want, and instead of asking you, it just assumes you want to do a continuous growth because we can then convert a continuous growth rate to an annual growth rate. And the basic idea is that they're close. The bigger the rate, the further they are apart in one versus the other, but they're still relatively close. So this model, what you might be missing over that circle is y equals a times e to the kx, which is still just a starting amount, which we're calling a. So a is the starting amount now instead of p. It's a lowercase a. The letters are arbitrary. You can write this 3 different ways, as you can see here. These are just 3 different ways to all write the same thing. A starting value times a growth factor raised to time. Starting value, growth factor raised to time. Starting value, growth factor raised to time. This is still that. It's still a starting factor times a growth factor raised to time, but the growth factor is this e to the k. K is known as the continuous growth rate. R is the annual growth rate. A is APR. I'm sorry, R is APR. Again, a little r is APR. A little k is continuous growth rate. They're close, but not the same. So in this format, the growth factor is no longer 1 plus r, it's e to the k. It's just a slightly different format. But the growth factor in one format has to match numerically the growth factor of another format, so we can set them equal to each other to go from a k to an r. But we don't know how to go from an r to a k. It requires some math that we don't know. Sorry if you can hear my dog barking. It's just a fun day. Hold on. Okay. All right, so then we're going to go to page 230 to 232 in the workbook. Again, just a couple notes. We know how to go from k to r, but not r to k. It involves logarithms. We're not doing logarithms. We're skipping that chapter altogether. And he's back to barking. Also, in your homeworks, if you ever see any problem that asks you to go r to k, skip it. If you ever see a problem that asks you about average percent change, skip it. It's above our pay grade. We're not doing it. It's in a chapter we're not covering. But they still somehow managed to shoehorn those problems into multiple parts of problems from chapters 6 or 8 or 9. And those are good problems, but I can't just say not to do part B, but you won't be graded. Don't worry. Same as with the midterm, we had one of those. All right. And I closed. Oh, man. Of course, I closed the one I need. This is just a fun day. Sorry you have to hear my frustration. I really could not believe when Zoom did that to me. But, you know, technology is always going to screw us over at some point, right? All right, so the point of this problem, if you read these instructions, read them on your own or pause, identify the continuous rate k, use it in a sentence, then compute the annual rate to 5 decimal places and rewrite the model. So again, we want to identify the k, which will then enable us to find the r to then write the model in the form that we would actually want to use. So annotate. And I'm going to skip showing some stuff in the calculator after doing it the first time. And I'm not going to do all 3 of these. I'm only going to do the first and the third in the interest of time. I'll leave the second one as an exercise for you, called your group work, right? So this right here is the k. The number in the exponent, when you see an e as a base, that's the k. So we know that k is equal to 0.1655. It's cookie cutter, because the model is y equals an initial amount times e to the kx. E to the k is the growth factor, k is the growth rate. Remember, rates are not factors. So now what we do is we set e to the k, the growth factor in one format, equal to the growth factor in the other format, which is 1 plus r. So we set e to the 0.1655 equal to 1 plus r. This e to the 0.1655, we just use our calculator to find that. We use our calculator to find that. Come on, let me go to calculator mode. Good Lord. So on, you have an e with an exponent right here. If you hit second and then ln, that's 0.1655. And we can see that number is 1.17998 to 5 decimals, 1.17998. So on the left, that's 1.17998 equals 1 plus r. To solve that equation for r, you're going to subtract 1 on both sides, which will give us 0.17998 is equal to r. As a percent, that's 17.998%. This is the annual growth rate. So a continuous growth rate of 16.5%. So in other words, we're gaining 16.5% every millionth, billionth, trillionth of a second, except we have to divide it by that million or billionth or trillionth of a time segment. So it is a really, really tiny amount in reality. But if you stack those up over a year, that means you gain about 18% over 1 year's time. The sentence that goes with this would be that the amount in the fund is growing by 16.55% continuously per year. Or you can say the amount in the fund is growing by 17.998% annually. Annually per year would be per year. And then the model that you can write for that in the annual model would be your future amount, A, or Y if you prefer, equals the starting amount. Now the starting amount is the same, it's always the coefficient. That's the starting amount. So it's 1200 times parentheses 1 plus, and then that 0.17998, and then raised to the time, which we're calling x for time now, t, whatever letter you like. You can go ahead and combine the 1 and the 0.179, so that's 1200 times 1.17998 raised to the x. This is the compound annually modeled. Again, this is what we would be dealing with homework, quizzes, tests, generally speaking. But Excel can only give us the exponential continuous model, so we have to know how to convert from one to the other sometimes. All right, so you can pause there. Let me go ahead and clear my screen. I said we're going to skip number 2. I'll give you a couple pointers. This 0.0036 is the starting amount. So that's the amount of people we had in the year 0. It doesn't make sense because we're looking at a population model and we're looking at it too long of a time spread. But we're only going to focus on later years, which is why our data points fit the model pretty well. This 0.0126 is the R. I'm sorry, is the K. I said the wrong letter. It's the growth rate continuously, which is going to be 1.26%. Then you can convert that to an R. You should get an answer that's almost the exact same thing. In fact, I'll tell you, it's 0.01268 when you round it to 5 decimal places. That's the R. It's 0.01268. Then you can make your sentences and convert to your new equation. With number 3, we'll do this one because this is going to be decay, because instead of this curve doing this, this is growth where we eventually have the explosion. Decay, it actually drops really quick at first and then flattens out to 0 because we're losing a percentage of something every time. Think about this. If you start out with 100 things and you lose 10% every year, after 1 year, you've got 90. The next year, you're not going to lose 10, though. You're only going to lose 9 because it's based on what you have. So now you're down to 81. The next year, you lose 8.1, so you're down to 73 roughly. So when you have 1 left, roughly, you're going to lose 0.1. When you have 0.1, you're going to lose 0.01. You're never going to hit 0 in theory. Now, of course, in the real world, you know, if we're talking about people, eventually it'll go away. Eventually, if we're talking about viruses, eventually it all goes away. But in terms of a model, you never actually hit 0. You just get really close to it. So with decay, K is going to be negative. We never associated R with being negative. We just did 1 minus instead of 1 plus in the model. So this 1 plus sorry, 1e plus 0.08, that's scientific notation, that's 100,000. This negative 0.139, that's our K, negative 0.139, or as a percent, that would be 13.9%, and that's a negative to signify that it's a decay. We're losing 13.9% continuously. So that sentence, I'm gonna skip the typing. Again, I'm really short on time. So just write it down, pause, rewind, all that stuff. That would be the US population, sorry. The safe listening time is decreasing by 13.9% continuously per decibel, not per year, because we're talking decibels, not time. So again, the safe listening time is decreasing by 13.9% continuously per decibel. Write that down. Now let's take that e to the k and set it equal to 1 minus r. Minus because it's decay. Be plus if it was growth. So that's e to the negative 0.139 equals 1 minus r. I gotta pull up my calculator. Come on, man. So on e to the negative 0.139, that's going to give us 0.8702. Let me just leave that calculator to the side like that. So that's 0.1. Why did I say 0.1? I'm rushing. 0.87023, and that's equal to 1 minus r. We are then going to subtract 1 on both sides, just like last time, but we won't be done. So if we subtract 1 on that, we get negative annotate. I miss y'all so much in person, I really do. 129.7. All right, that was originally 3, so 7, yep, equals negative r. But now we have to divide both sides by negative 1, because that says negative r equals. So that tells us that 0.12977 is our r, or 12.977% is our annual decay rate. So we're losing 12.977% per year, about 13. As a continuous rate, it's about 14% continuously. As an annual rate, it's about 13% annually. The continuous rate, if you look at exactly 1 year's number, you lose the annual amount. So this 13.9% continuous loss translates to you losing 12.977% exactly over 1 year. All right. Take off annotate. And let's go back to our notes. I need to clear my screen. And take off annotate. So these two formulas we've already seen. They're the first two formulas on your formula sheet. I attach these statements to them so you know exactly what to do. If you know the starting amount but not the ending amount, you use one of these two. How do you know which one? Are you compounding annually, or are you compounding more than once per year? Read the question, read the question, read the question, read the question, read the question. Pay attention, pay attention, pay attention. That's where students go wrong. They don't pay attention. They just go, oh, I want to use this formula. No, you got to pay attention. All right, but there is a third formula that we're about to set up and see some examples with down there. What if you don't know the starting value? What if you know the ending value? You want to know how much you start with. So maybe you see how much you have in an account, but it's been 30 years and this account has changed hands from company to company. Like you went from Crestar to SunTrust to now Truist, and they don't have any of your original records because of this. So what did you put in to just sit aside for 10 or 30 or 40 years? Well, you can use this formula if you're compounding in times. Now, what if it's compounding annually? Can we not use this formula? Well, sure you can. You just make the n a 1. Oh, please don't ring my doorbell. So again, if you wanted to use this formula, but it was compounding annually, just let the n be 1. How did this formula come about? It's you take this equation A equals BC and you divide both sides. by C. C is the parentheses here. So if you divide both sides by that parentheses, this 1 plus r to the t, or this 1 plus r over n raised to the nt, basically the parentheses just goes under the a. So the C, again, is representing me dividing both sides by the parentheses. That's how this is derived. These two formulas right here are literally the same thing, just algebraically rearranged. So, example, again, notes are already up here. Sorry for that. I'm doing the best with what I can. Bob has $37,000. I can at least not show the answer. $37,006.11. He deposited this money into a 4% compounding annual account 10 years ago. Has no idea what he started with. Let's figure that out. So since he's compounding annually, we're going to have to let the n be 1. So that's what I said. Compounding annually means n1. N is 1. If I said compounding monthly, it's 12. If I said compounding daily, it's 360 or 365, depending on what the problem says. If I say compounding quarterly, it's 4. The 10 is the t, or our x, if you will. This 37,000 and some change is not the starting amount. It's the ending amount. Label your stuff. 4% as a decimal is 0.04. So we use that formula I just gave you because we know the ending amount, not the starting amount. So this is the formula we use. 37,000 is the ending amount. The r is the 0.04. The n is 1, so that goes in there twice. The t is 10. 10 times 1 is 10. Dividing by 1 does nothing. And then if you type this number in a calculator, I'll at least show that work. 37,006.11 divided by, open a parentheses, 1 plus 0.04, close it, raise it to the 10th. You have got to practice with your technology. If you think watching me is going to help you, it doesn't. I mean, it does a little. It gives you an idea of what to type, but your calculators are probably different than mine for some of you. So you've got to learn how to use your calculator. Some of you might feel like you have to do this in multiple steps, but most scientific calculators can knock this out all in one. And there's our 24999.99. Rounding that up, that gives us $25,000. So Bob had put away 25 grand. Ask yourself, does this make sense? You always ask yourself, does this make sense? You don't just go on to the next question. You say, hey, is this right? Otherwise, if I'm your boss, you give me a wrong answer, I'm firing you, right? So ask yourself, does this make sense before you turn it in and get fired? Well, yes, it makes sense. If we're gaining money for free, if we got 37 now, 10 years ago, we should have had less. 4% is not a massive interest rate, so I don't expect this to just be a few bucks. It's probably a little closer to where we're ending with. All right. So I know that was super fast. I did not have a choice, unfortunately, because I need to get this video up. As a reminder, this was just 6.1 finishing it, and then 6.2. You have all this stuff for due dates. You have a quiz coming up. Please make sure you knock that out. I'm really hoping that Zoom isn't just going to be silly again. I wanted to say another word. Hopefully it records this video so that I can upload it. Again, I am very sorry for this abbreviated version of the notes. If I had a choice, I wouldn't be doing it this way. Technology messed me up. And I don't even know why. My fingers are crossed it doesn't happen again. So good luck with this stuff. We'll see you on Monday, hopefully with less issues. All right. Stop share. End meeting.